Hello, my name is Marissa, and today I'm going to be talking about population dynamics of sea otters on the west coast of the United States. So, what is population dynamics? Population dynamics is the study of how and why the size of a population changes over time. It can be used to examine and manage populations of all kinds of life forms. For many species of animals that are endangered, it is used to help protect them and their resources. Knowing how the population changes and what affects it allows conservation scientists to take the next steps in protecting plant and animal species. Now, why are sea otters important? The southern sea otter is currently one of many endangered species that live along the western coastline of the United States. Sea otters are a big help in controlling the population of sea urchins, who are very destructive to kelp forests. These kelp forests support a greater diversity of species by providing shelter and food to ocean animals. Without sea otters, many other marine species would fail to survive, and entire ecosystems can die. Therefore, ways to monitor and manage their population is necessary. There are many different mathematical models that can be applied to population dynamics to predict population abundance and expected growth rates. One of them being a differential equation. Now, a differential equation contains a function, which could be a population at a certain time, and its derivatives, which usually is the rate of change of the population. A derivative is the slope of the function, or how fast something increases or decreases. The rate of change of a population can depend on many factors, one of them being the initial population of a species. A differential equation describes the relationship between the abundance of a population at a certain time and the rate of change. So, how does it work? One model that is often used to represent the expected rate of change in a population is the logistic growth model, where N is the population or the abundance, K is the carrying capacity, which is the number of organisms an ecosystem can support, and R is the maximum growth rate. As you can see here on the right side, we have dN over dt, which is the differential equation. Now, this model shows the growth rate R is linear and is decreasing in terms of N with respect to time t, as you could see on the example graph on the right. This is usually how logistic growth models look like. R is going to be at the steepest part of the graph. R, remember, is the maximum growth rate. So it's going to be where the population size is changing at the fastest rate. The carrying capacity is a limit of the population size, and that usually comes from predation or available resources, or just because there's limited space in the environment. But there's other limits to this model. Sometimes populations rapidly or slowly decline as it approaches the carrying capacity. This model doesn't realistically represent the rate at which a population approaches the carrying capacity, because every population is different. A study done in Washington State on the population dynamics of sea otters uses a more flexible version of this called the theta logistic growth model. Theta, which is the little symbol in the right corner of this formula, controls the curvature of the growth rate. So with a higher theta, you have a steep decreased rate. A lower theta is a more steady decreased rate. The log transformation that is at the front of this formula is used to remove or reduce skewed data. Now, this symbol that looks like an upside down Y is lambda. And in this study, lambda is the expected annual growth rate, and it's represented by a differential equation, and that is dN over dt, and this is the theta logistic growth model. Now, here on this slide, I have an example of different values that were put in for theta. And the maximum growth rate in this graph, R, is 0.5. K, which is the carrying capacity, is 100. Now notice that when theta equals 1, R is linear, and this gives us the basic logistic growth model. Once the growth rate reaches 0.5, or when the population reaches 100, the growth rate declines. So as you can see here on the left, when theta equals 1, we have a straight line. When anything other than that, once we reach 100, it is either really steadily decreasing the rate, or it is very steeply, rapidly decreasing. So as the population approaches K, there can be a rapid, very rapid decrease or a slower, steady decrease. When theta is greater than 1, there is a rapid decline. When theta is less than 1, there is a slower decline. This theta allows researchers to fit their data to a more accurate model. As you can see here on the right, we have K on the bottom, or K as that really dark dot, and as N, as the population size is approaching K, you can see if theta is 0.5, you have more of a steady decline, versus if theta is 10, you have a really steep decline in the growth rate. Now, using this model, the researchers in Washington State with the sea otters were able to forecast the sea otter population abundance to increase over the next 25 years. According to the article, though, this increase in population has potential to increase sea otters' competition with state and tribal shell fisheries, which should be studied more. On the right here, you can see a graph of the results. It started out as around 2,000 independent sea otters, and by 2044, it is projected that we'll have more than 4,000 independent sea otters. Now, there are more studies being done to see how different resources and elements to the environment affect the population of sea otters, some of them being like predation and competition, as I previously stated, or sometimes climate change or topography. This model can be used as a template for the recovery of other endangered small species populations, since it is shown that they are going in the right direction here in this study in Washington State, with population projected to be generally increasing. So this model can be very helpful to other populations.